In this lab, we're going to be looking at metamorphic rocks. Metamorphic rocks are those formed when we take an existing rock, we subject that rock to conditions that are different from the conditions under which the rock was originally formed. That might be an increase in pressure, an increase in temperature. It could be exposure to chemically reactive hydrothermal fluids. The result of these new conditions is that the minerals that were originally in that rock become unstable because of the higher pressures or temperatures they're being subjected to. That causes the mineral texture to change, both size of the crystals and also the way the crystals are arranged. And also some of the minerals recrystallize into new types of minerals that are stable under the higher pressures and temperatures accompanied by the metamorphism. Of course, if we continue to increase in pressure and temperature, eventually we start to melt the rock, we form a magma, and we then moved into the realm of igneous processes. The result would be an igneous rock. In metamorphic rocks, we're talking about recrystallization of minerals that were low pressure and temperature into both larger mineral sizes and new types of minerals that are stable at higher pressures and temperatures. But that crystallization, recrystallization takes place in the solid state without actually melting the rock. Now, in working with our metamorphic samples, we're going to be considering both the texture and types of minerals. Texture would be size of the mineral crystals and also the way those mineral crystals are arranged with respect to each other. Metamorphic rocks that form under conditions where we have a directional pressure, a pressure that is greater in certain directions, those minerals tend to take on preferred arrangements. That preferred arrangement or orientation is called foliation. In other words, the rock has a noticeable grain. The mineral crystals are all aligned in the same direction, representing a pressure that was applied like so. The result, the purpose of foliation from the rock's perspective is for the mineral crystals to be oriented in such a way that the maximum pressure is distributed across the largest possible surface area, the largest face of that mineral crystal. So the crystals orient such that their largest face is perpendicular to the maximum pressure. That results in a foliation, a preferred alignment or arrangement of the mineral grains. Foliated textures are very different from igneous textures, which, as you can see, the mineral crystals are randomly oriented. There's no grain to that rock, no preferred orientation, reflecting the fact that the rock crystallized under a uniform pressure field. Pressure was equal in all directions, resulting in no preferred orientation to the mineral crystals. Our foliated metamorphic rock formed under conditions where the pressure was greater in certain directions, causing the minerals to take on a preferred alignment or foliation. Now, foliated textures are only seen in metamorphic rocks, but not every metamorphic rock is foliated. So we're going to start by thinking about which of our rocks are foliated and which are not, which have preferred orientations and which do not. Well, this one obviously does, as does this one. Also a distinct grain to the rock. At smaller crystal sizes, foliation can be a little bit harder to recognize. In this rock, there is still a preferred orientation or grain called foliation to this rock, reflecting pressure that was applied, something like that. This is still a foliated metamorphic rock, as is this one. Preferred orientation to the mineral grains, giving the rock a grain, if you will, preferred orientation to those mineral crystals. Now, foliated textures develop when the rock has flaky or flat-shaped mineral crystals like micas. Micas are very skinny in one direction. They're sort of shaped like sheets of paper. because they have unequal size faces, micas can take up foliation. They're going to orient so that their largest face is perpendicular to the maximum pressure. Foliation also occurs when the rock has needle-shaped minerals, minerals that have a long axis. The long axis is again perpendicular to the maximum pressure. So foliation develops when the parent rock supports the formation of platy-shaped minerals like micas or needle-shaped minerals like amphiboles. In other words, the composition of the parent rock undergoing metamorphism has the right elements to make minerals like micas, biotite, and muscovite, or needle-like minerals, amphiboles, such as hornblende. Texture is also thinking about the size of the mineral crystals. In this rock, the individual mineral crystals are very small. They cannot be seen with the unaided eye. It requires magnification to see the individual mineral crystals. There are micas present in this rock. Remember that mica minerals like biotite and muscovite have glossy, vitreous lusters, so the rock has the sheen that we associate with mica minerals. And because those small mica minerals are flaky in shape, the rock is foliated. There's a grain, a preferred orientation to those mica minerals. This is also a foliated metamorphic rock. Smaller textures, smaller grain size than this. Here we have large mica minerals. Here we have small mica minerals, but in both cases, the rock is foliated. This is also a foliated metamorphic rock. Similar types of minerals to this one, but now a larger proportion of dark-colored mafic minerals, amphiboles, and a smaller proportion of light-colored minerals like feldspar and quartz. This foliation is called banding. It's the foliation that we associate with the metamorphic rock gneiss. That banding occurs as the light and dark-colored minerals segregate from each other. The dark-colored minerals, amphiboles, have a long axis, an axis, one dimension that's greater than the others, so those amphibole minerals take on foliation. The light-colored minerals are minerals like quartz and feldspar. They have more equal dimensions to the mineral crystals. They're non-foliated. But nonetheless, they're segregated because our dark-colored minerals are foliated and segregated into bands. And that occurs as higher amounts of pressure and temperature are applied to the rock. Here, we have a relatively modest increase in pressure and temperature. Mica minerals like muscovite, biotite, or the green-colored mica chlorite are still stable. They're just growing larger. But at even higher pressures and temperatures, those mica minerals are unstable. They're replaced by denser, more compact amphibole minerals. As that happens, the mafic minerals are squeezed into smaller and smaller bands as the blocky, light-colored minerals, quartz and feldspar, continue to grow. Those light-colored blocky minerals are present here, but they're still relatively small and difficult to see. With continued metamorphism, those light-colored minerals grow larger, and our mafic minerals change from micas to denser amphiboles that are squeezed into more compact and smaller bands. So the type of foliation is indicative of the intensity of metamorphism. How much pressure and temperature did the rock experience? This banding develops at the highest pressures and temperatures, the most intense metamorphism. Large mica minerals develop at intermediate amounts of pressure and temperature. Pressure and temperature is increased significantly large mica minerals are formed, but not too much pressure and temperature has been applied because the mica minerals are still stable and haven't been replaced by amphiboles. So a metamorphic rock with large mica minerals represents an intermediate amount of pressure and temperature, an intermediate grade of metamorphism. Smaller mica minerals reflect smaller amounts of pressure and temperature, a lower intensity of metamorphism, a lower metamorphic grade. So we have low grade, mica minerals are small, intermediate grade, mica minerals are large, high grade, mica minerals have been replaced by amphiboles. So the type of foliation and the grain size, as well as the type of mineral, mica or amphibole, reflects the intensity of metamorphism from low to intermediate grades to high grades of metamorphism. Our other metamorphic rocks here are composed mostly of a single mineral. That single mineral is blocky shaped, resulting in no foliation, no preferred arrangement to those mineral crystals. That occurs when the parent rock is mostly composed of one mineral. For example, limestone, the mineral calcite, recrystallizes during metamorphism into larger, more compact grains of calcite. Sedimentary rock sandstone, composed of sand-size quartz grains. Metamorphism causes those quartz grains to become more compact and interlocking, but remain quartz grains, producing the metamorphic rock quartzite. Both of these rocks are non-foliated in texture. One is composed of calcite, the metamorphic rock marble. The other is composed of quartz, the non-foliated metamorphic rock quartzite. How would you tell the difference between a metamorphic rock of calcite and a metamorphic rock made of quartz? Well, the texture is very similar. There is a difference, but it takes a practiced eye to see that difference. What would be more obvious is that the metamorphic rock made of quartz has those sharp edges that we associate with silica-rich materials, like glass. Sharp edges, conchoidal fracture. That is our metamorphic rock made of quartz. Because it's quartz, it will also be harder. It will scratch more of our test objects. It will scratch glass. It will scratch the streak plate, reflecting the higher hardness of quartz. The metamorphic rock made of calcite, lower hardness, probably will not scratch the glass, certainly will not scratch the streak plate, lacks the sharp edges of quartz-rich material. And to confirm that it is made of calcite, you can try putting a few drops of the dilute acid on it. If it's made of calcite, you'll witness a reaction caused as that calcite dissolves and CO2 gas is given off. You'll see fizzing of the rock as the CO2 gas is released. So in working with our metamorphic rocks, let's think about, first, is the rock foliated or non-foliated? Does it have a preferred orientation or grain or not? If it's foliated, we need to further describe the texture in terms of grain size, size of the mica minerals, size of the amphibole minerals, and whether that foliation gives the rock a banded appearance at the highest grades. For non-foliated metamorphic rocks, we lack a distinct texture to help us name the rock. Instead, we have to think solely about composition. Is the rock made mostly of quartz, in which case it'll show sharp edges and conchoidal fracture, higher relative hardness, or is it made mostly of calcite, lower relative hardness, lacking sharp edges, and will show reaction or fizzing when acid is applied?